solutions to the Chapter 10 homework was due today, February 27th, 2026. We actually went over most of these in class, but just to recap, or if it helps you, essentially we have, for 21, we had a spring that was had a spring constant of 25 newtons per meter. It was compressed 0.1 meters. Oh, that sounds not good in chemistry. Something just broke. And it ended up being, basically, once it was compressed by 0.1 meters, then when it was released, it ended up moving 25 meters per second. So essentially then it's saying, well, what happens if you have the same 1 kilogram object and it was squished 0.1 meters, but now you had two springs side by side or in parallel? Well, in this particular case, when we have two springs, they each have a spring constant of 25 newtons per meter, and therefore that acts like a single stronger spring with a spring constant of 50 newtons per meter. So if it's squished the same amount, which is 0.1 meters, and we have 50 newtons per meter as our effective spring constant, then that would equal the initial spring potential energy. The final kinetic energy would have been double to what it is before, and therefore the final velocity of this block would be radical 2 times greater. So it would be about 0.71 meters per second. For problem 22, when we have the springs in series, essentially they become weaker. Why? Because 25 newtons would stretch the first spring and the second spring by 1 full meter. So in series, that stretch would be 2 meters. And therefore, the spring constant is effectively only 12.5 newtons per meter. So it takes less force to stretch when they're put in series. So now we're going to think of this situation where it's 1/2 12.5 newtons per meter times 0.1 meters squared equals 1/2 mv squared at the end, and that velocity would be about divided by radical 2 instead of multiplied by radical 2. So essentially it's about 0.355 meters per second. For problem 52, so this we had at the bottom, it was squooshed by 0.3 meters. They gave you the spring constant, which I think was 500 newtons per meter. I can't even read my own writing. Mass of 2 kilograms. Yep, so then it's asking you, if this thing goes up 1 meter to get to a truck, what speed would it get to the truck? And if this is frictionless, we have initial spring energy goes to gravitational potential energy and kinetic energy. So I have my initial is equal to my final of these types of energies, and I get that it enters the truck at 1.7 meters per second. For part B, I end up then saying, well, now what happens if we have a situation where we have friction down here? So we have work done by friction would be subtracted off from the initial energy. Well, that initial energy we found earlier was 22.5 joules. So coefficient of friction times mass times g, so that's the normal force, times that distance, so that's how much I would lose, and that would equal my final energy. So essentially I did not do that right, I think. Oh, yeah, I did. So essentially I lose 2.94 joules of energy due to friction. That's the negative amount of work that is done. So I'm left with 19.56 joules. But to get up this height, 1 meter, takes 19.6 joules of potential energy. So it's going to fall just short of reaching up to the truck. Problem 54 we did in class. So there's a couple ways to do this I talked about. But essentially then for part A was pretty straightforward. The initial spring energy equal the kinetic energy just after the push. So that ends up being 14.1 meters per second. For part B, though, we have the initial energy up here, and you could either say subtract off the work done by friction or the work done by friction and gravity, and that would equal 0. Or you could say initial energy minus the work done by friction equals the final energy, which would equal kinetic energy. So essentially here, what I could have said, I'm going to shrink this down. we could have said, I'll do that down here. U spring plus U grav minus work done by friction equals U grav. I will make that smaller still. So I think that fixes that. So that goes the black ink with the black writing up here. I did this. So essentially, my initial energy was 19,800 because it's spring energy plus gravitational energy. I lose energy due to friction acting downhill. I lose energy to the parallel component of gravity acting downhill. So I subtract those off. How do I find out that amount of work? Well, that's that force times distance. So I get that the force is essentially, friction is 127 newtons. The force of gravity is 490 newtons. Both multiplying those by the distance it goes up the hill. And so I get around 32 meters. And then here I tried to fix this. It doesn't look very good. So it should be 19,800 minus mu mg cosine theta d equals mgh, but h is equal to d sine theta, so this would be equal to mg d sine theta, which is also what I have up here. So, okay. And I think, yeah, hold on for a second. Extra problem, and again, I went over a lot of this in class, but it is super helpful to look at it. Sorry some of the scanning didn't look great down here with the ink that I used, but you're given this velocity time graph. You're asked to figure out the acceleration graph, so basically that's the slope of this graph. So we get plus 10, minus 10, and 0. Here, you're asked to figure out the position versus time at each second. So we start at 0 meters. Thinking about the shape, I would be concave up for positive acceleration, concave down for negative acceleration, linear for a constant velocity at the end during the last 1 second. So I get after 2 seconds, I get 20 meters. After 3 seconds, I get 35 meters. After 4 seconds, I get 45 meters. And this is using variations of kinematics equations. So for C, I ended up getting kinetic energy versus time. So I just plugged the velocities in after every 1 second. 1/2 mv squared, and the mass was 0.5 kilograms to get the kinetic energies. For letter D, was asked to have the force versus time graph. So if I know Newton's second law, F equals ma, then I can essentially have the 0.5 kilograms times the acceleration in this graph, which was the graph for part A, and I get the forces. For E, to find the impulse, impulse is force times time interval. So that's plus 10 Newton seconds from 0 to 2 seconds, negative 5 Newton seconds from 2 to 3 seconds. I think I may have asked from 2 to 4, but there's only a force from 2 to 3. For F, you're asked basically to figure out the speed at the end of 2 seconds and 4 seconds using impulse momentum theorem. So we start with 0 units of momentum. We add 10 units of impulse from 0 to 2 seconds. We end up with, therefore, 10 units of momentum after 2 seconds. P equals m times v. So something like that. And we end up figuring out that we get 20 meters per second. So 10 units of momentum is 0.5 kilograms times v. I don't know why I forgot a parenthesis around here, but I did. And then from 2 to 4 seconds, actually, we have negative 5 Newton seconds of momentum. So from 0 to 4 seconds, we have 0 plus 10 minus 5. So at from 2 to 4 seconds, we have 5 Newton seconds, or 5 kilogram meters per second of net momentum. So that's P equals mv, which I did write down here. 5 equals 0.5 times v at 4 seconds, and that's 10 meters per second. So the energies, work, and velocities all agree with the original graph. For letter G, end up having figuring out a force versus position graph. So I have 105 newtons, during the first 2 seconds. Well, after 2 seconds, I'm at 20 meters. So I have positive 5 newtons for 20 meters. I have negative 5 newtons of force from 2 to 3 seconds. Well, after 3 seconds, I'm at 35 meters. So I have negative 5 newtons from 20 to 35 meters, and then 0 newtons from 35 meters to 45 meters. And so here, if I'm looking to find essentially this work done, it's the area of a force versus position graph. So for the area from 0 to 2 seconds, that's positive 100 joules. So the work is 100 newton meters. From 2 to 4 seconds, the area is negative 75 joules, so the work is negative 75 newton meters. Technically, this all happens between 2 to 3 seconds, but it's also from 2 to 4 seconds. So from 0 to 4 seconds, the net work is plus 25 joules, or plus 25 newton meters. For letter I forgot to do this one thing, which is essentially to say KE equals 0.5 m times v squared. So I should have done this to get the velocities at the end. When I do that, it basically is what's the same thing that happens up here. So after 1 second, or pardon me, after 2 seconds, I end up having 100 joules, and after 4 seconds, I end up having 25 joules. And so that would basically give me 20 meters per second here, 10 meters per second here. So anyhow, that's how I would get that. So hopefully those help. Hopefully you see how some of these things interact with each other, because that's kind of where we should be at this point of the course. Thanks.